Okay, in this video we're going to talk about velocity versus time graphs. And we're going to start with an example. And what we have displayed here is a position versus time graph. And you can see at time 0, we start at 0 over here, and in 2 seconds we increase to 3 meters. Then we stay put until 3 seconds, and then we go back down to -2 meters, and then we go along this parabolic path here, and we end up back at 2 meters at 6 seconds. So what we're going to do is we're going to find the velocity at various intervals. So the first will be from 0 to 2, then 2 to 3, 3 to 4, and so on. Okay, so let's look at that first interval. Now, what we want is the average velocity over that time interval. So if you recall that we can get the velocity from the slope of the tangent line. So let's compute that. So the slope is equal to the rise over the run, or in our case, the change in x over the change in time. And we get, well, a change in x, we go all the way up to about 3 meters, and we go over 2 seconds. So the change in x is 3 minus 0, and our time interval is 2. This is in meters and seconds, so we get 1.5 meters per second. So that's the slope of the line, of this line right here. And if you recall, the slope is just our average velocity. Okay, now let's go to the next time interval. So the next time interval is from 2 seconds to 3 seconds, and if you see, the position doesn't change at all. It remains constant. So if we consider the slope of this line in this interval, it's just equal to 0. So the velocity of this particle, or whatever it is 0 from 2 seconds to 3 seconds. Then all of a sudden, the position starts changing, and this object starts going backwards. And we can compute the slope of that line. It's just, well, the change in x is equal to, our final position is -2, and our initial position is 3. So we get -2 minus 3 over 1 second. The top is in meters, so this is going to give us -5 meters per second. Okay, now let's look at the interval from 4 to 6. So that's the time interval from 4 to 6. Now this isn't a straight line like the previous cases over here, here, and here. What we have is a parabola, and what we can do is look at the instantaneous velocity at any particular point along here. And there's one point that's the most interesting, and that's this point right here. At that particular point, if we were to draw a tangent line to that curve, we would get the following. We get this line like this. And that is a horizontal line. The slope of that line is just equal to 0, much like it was over in this interval from 2 to 3. So at this particular point, the slope of this tangent line is equal to 0. So at t equals 5 seconds, the slope of our tangent line is 0. So the velocity at that particular point is 0. And if we look what's happening from 4 to 5 seconds, if we were to draw various tangent lines, you would notice that they get less steep the closer you get to 5 seconds. So we can draw a few of these. as we get closer to 4 here, our tangent lines get steeper and steeper. So the velocity of this object is decreasing to 0. And then on the other side, it continues to decrease, but it becomes negative. We'll see what happens to that curve down below. So what we're going to do is we're going to plot velocity versus time now in another graph. So I've already drawn those axes down here, and we can now draw the graph. So let's look at the first interval from t equals 0 to t equals 2. We have a slope, or rather the velocity is constant over that time interval because we have a straight line. It's linear, it's linearly increasing, and the slope of that line was 1.5 meters. So that means the velocity for the first 2 seconds is, well, 1.5 meters. So we can actually plot that. Oops. Wait. Oh, why is that not working? There we go. Alright, so let's plot that. The first 2 seconds, there's our line. It's a straight horizontal line because the velocity is constant over those 2 seconds. Alright, let's go back up. Let's look at the interval from 2 seconds to 3 seconds. The slope of that line was 0. So the velocity in that time interval is 0 always. So if we go back to our graph, we can plot the velocity in that time interval just like, oops, that's not very horizontal. Let me draw it again. That's close enough. Okay, now from 3 seconds to 4 seconds, the slope of the line, again it's linear, the slope of the line is -5, and it's -5 over that whole second. So we can go back to our velocity versus time graph and plot -5, which is 2, 3, 4, down here. Okay, finally, let's look at this parabolic motion from 4 seconds to 5 seconds. 4 seconds to 6 seconds. We know at time equals 5 seconds that the velocity is 0. So our whatever our velocity looks like, it should be 0 right there. Okay, so what next? Well, we know just after 4 seconds the velocity is going to be positive. And I'm not going to actually figure it out because we didn't before, but it's going to be something positive. The point is, at 4 seconds, it's going to start somewhere up here. I don't know exactly where, but we could figure it out. We could draw a tangent line and so on. But let's just qualitatively look at this. And because this is a parabola, the position is a parabola. The velocity over here at 6 seconds should be the same at 4 seconds, but negative. So whatever it is, at 6 seconds, it should be somewhere down here. Okay, so because this is a parabola, it's nicely behaved, it's nice in a continuous curve, we can actually plot the velocity as a straight line, well, a straight line with some kind of slope to it. We know that it goes from being positive and getting smaller and smaller all the way to 0 at 5 seconds, and then it continues to get decrease and gets more negative all the way to 6. So this is our velocity versus time graph, and note the discontinuities here. Very few objects actually sort of travel like this, instantaneously go from some positive velocity over here to a 0 velocity in an instant. But this graph is a good example of just plotting simple position and velocities using nice, easy values. So what we can do is, if you're worried about connecting all of the positions here, we can just connect them with, oops, I didn't want to do that, with a dotted line. So over here, but these are discontinuities. For instance, if you're driving a car, you wouldn't expect in an instant to go from some positive velocity to zero. Your car would probably break. Okay, so there's our velocity versus time graph, and here we're always taking advantage of what we are given in the position versus time graph. Alright, now our velocity versus time graph actually gives us information as well. If we note, especially from 4 seconds to 6 seconds, the velocity is changing, and it changes linearly. So the slope of that line actually tells us something. It tells us it gives us something about the rate of change of velocity. Just like in position versus time, the rate of the change in position versus time gives us the rate of change of position. I just said that. Okay, so the rate of change of velocity is acceleration. Okay, so actually, instead of using this graph, why don't I delete this? And what we'll do is we'll copy this graph here, just so we have it. Okay, there we go. Okay, so here's our velocity versus time graph from above, and what we're going to do is we're going to use it to figure out acceleration in these various time intervals. So let's just label a few of these times. This was 1. Hold on. This is 1, 2, 3, 4, 5, and over here we have 6. Great. Okay. So what does the acceleration versus time graph looks like? Well, let's draw a graph. So if you just bear with me for a minute or two, I'll get an axis going here, and there we go. Okay, let's plot it. Here is our graph. You know what? I want to make it bigger. And I want it lined up more. Alright, there we go. Okay, so this is our acceleration versus time. Time is in seconds. Our units for acceleration in this case are meters per second squared. Okay, so we're going to plot acceleration using our velocity curve or graph. Now let's look at the interval from 0 to 2. In that interval, the velocity doesn't change. The velocity was constant. And if we're looking at acceleration, remember acceleration is a change in velocity over a change in time. The change in velocity here is 0. So we can write, well, rather the slope of this line is equal to 0, and that's what our acceleration is. So we can plot acceleration down here. On this interval from 0 to 2, we get nothing. Okay. In fact, the same is true for the interval from 2 to 3. The velocity is constant here. There's this discontinuity, but from 2 to 3, our velocity is not changing. So we can continue this line, make it all 0, like that. Okay, so here we have the slope is 0. Oops. In fact, the slope is 0 from 3 to 4 as well. So this is not a very interesting velocity versus time graph yet. I mean acceleration versus time graph, because it's 0 for the first 4 seconds. But let's look at what happens from 4 to 5 seconds. From 4 to 6 seconds. Here, velocity is changing. We can write acceleration as the change in v over the change in t. Our change in v, we go from, oh, I didn't even pick values here. Let's say, I don't know, 1, 2, 3, 4, 5, 6. Let's say our change in velocity is from minus 6 to 6, or rather from 6 to minus 6, and that's over 2 seconds. So that's meters per second, and, well, what do we get? We get minus 6 meters per second squared. So that's the slope of this line over here. So, I didn't draw enough lines here on our graph, but we can continue this down, and we get a line from here, the horizontal line, sorry, like that. And again, if you're worried about the discontinuity, it's okay. You can draw a dotted line to represent the discontinuity. So there is the acceleration versus time graph for this velocity versus time graph, which we obtained from our position versus time graph up here. Notice that to go from position to velocity and then velocity to acceleration, we were always looking at slopes of lines or slopes of tangent lines, and that's generally how you do this kind of thing. We can go in reverse. We can, given an acceleration versus time graph, plot a velocity versus time graph and a position versus time graph. So why don't we do a quick example of one of those. So I just need to grab another axis here. Again, just give me a moment. Oops. And let's see, go all the way to 7. Alright, so let's plot this curve. There we go. And this will be our acceleration in meters per second squared versus time in seconds. Okay, and let's just make up some values here. Let's say from 0 to 2 seconds, we have an acceleration of 2 meters per second squared. And from 2 to 3, we have 0. Oops, that doesn't look like 0. Okay, and then from 3 to 4, we'll have, let's say, minus 1 for an acceleration. Actually, let's go all the way to 5. Make it a little more interesting. Okay, so there's our acceleration versus time graph. And what we're going to do is look at how we can take this information and plot a velocity versus time graph. Okay, we're going to assume a couple of things. The first thing is we're going to start at x equals 0. So our initial position is at the origin, and we're also going to assume our initial velocity is 0 as well. This will help us plot the next graphs. Alright, so we're going to need another axis because we're going to plot the velocity versus time graph now. Alright. There we go. And we'll label this. Always label your axes, by the way. So this is our velocity axis, which is meters per second. And we have time in seconds down here. Okay, So, how do we get velocity? Well, we know we start at 0. So our velocity curve starts here, and we know that the acceleration is constant. And that means we can actually figure out what the velocity should be at 2 seconds. We have to use our kinematics equations. So let's do that. We know that acceleration is equal to a change in velocity over a change in time. Now our change in velocity is our final velocity minus our initial velocity over our change in time. And what I'm going to do is I'm just going to solve for the final velocity. The final velocity is equal to our initial velocity plus the acceleration times delta t. Okay, now for this particular interval, the initial velocity, this vi, is 0. We're starting at 0. So this first term is 0. Then we just have acceleration times delta t, and delta t is 2 seconds. It's the length of our time interval. That means that at 2 seconds, our velocity should just be the product of the acceleration times time, which is 2 meters per second squared, times our time interval, which is 2 seconds, and what we get is 4 meters per second. So we go from 0 all the way to 4 at 2 seconds. So that's this point right here. And we can plot that using a straight line. Why is it a straight line and not a curve? Well, because we have constant acceleration. Our acceleration is the same everywhere. That means the slope of this line should be the same everywhere, because acceleration is related to the slope of our velocity curve. Okay, so next we go from 2 to 3. If we look at 2 to 3, the slope of this line is 0. That means the acceleration is 0. If the acceleration is 0, the velocity is not changing. So in this interval from 2 to 3, we actually have constant velocity, like that. And finally, from 3 to 5, we have negative acceleration. So how can we get the change in velocity? Well, we use the same equation we had up here. Okay, so remember, our final velocity is equal to our initial velocity plus the acceleration times delta t. Now our initial velocity is 4 meters per second. Our acceleration in this case is minus 1 meter per second squared. And our time interval is 2 seconds. So if you look at this, it's 4 plus minus 2, which is 2. And that's in meters per second. Note that this second cancels with one of these. Alright, so essentially we go from 4 seconds down to 2 seconds at time equals 5 seconds. We go from 4 meters per second to 2 meters per second in 2 seconds. We can plot that just like this. There. Okay. That's all the information we can actually plot here. But there's something to note. Look at what we got back here. This 4 meters per second. We multiplied the acceleration times the time. So the acceleration is this 2, so and the time was the 2 seconds. So in fact, it was 2, the height of this, or this length here, times this length, which is the area underneath our curve. So here the area is equal to 2 meters per second. Sorry, not 2. My bad. It was 4. So the area underneath our acceleration curve, or at least the area between the curve and the horizontal axis, gives us the change in velocity. So the area, oops. Okay, so what about from 2 to 3 seconds? Well, there's no area there, right? There's the line is right on the x-axis, so the two lines overlap. There's no, it doesn't mark off any area. So our delta, our change in velocity is 0, which is what we see here. What about from 3 to 5? Well, now the line here is below the t-axis, or the horizontal axis, but the area between the axis and the curve actually still tells us something. So let's just shade that in. Because it's below the horizontal axis, the area is actually negative, and the area, or yeah, we can treat it as negative, and the area in this case, well, it's minus 1 times, or 1 times 2, so it's 2 meters per second, but because it's below, we treat it as negative area, and so the change in velocity is minus 2 meters per second. So we go from 4, we have, wherever we end up at 5, it has to be 2 less, so that's at 2 meters per second over here. Okay, so that's how we can go from an acceleration versus time to a velocity versus time. And in fact, we could do position as well. We can get position from our velocity versus time graph in pretty much the same way we just got velocity from acceleration. So let's quickly do this. I need another axis here. I'm just going to freehand this. It's not going to be as nice. So there's my horizontal, my vertical, and my, oh, you know what? It's going to be mostly positive. Let's go over here. Okay. So there is our axis. The vertical is our position in meters, and our horizontal is time in seconds. Alright, we have 1, 2, 3, 4, 5, 6. Okay, so in the first 2 seconds, if we want to figure out the change in position, we look at the area under our curve. Now this is the area of this triangle here. So the area is equal to 1/2 times the height, the change in height. Now the height is 4 meters per second, and the time is 2 seconds. So we actually, the area in this case is 4 meters. So the change in position is 4 meters, and we were told back here that we're starting at the origin. So that means we start here and we increase up to 4. So 1, 2, 3, 4. And the first 2 seconds we Go all the way up. Well, that doesn't look very good. Let's draw a straight line. Go all the way up to 4. Alright, now I have done something wrong here. If you look at this purple line, it's a straight line indicating that the velocity is constant. But the velocity is not constant. It changes. So this is not a straight line. What we should have drawn is a parabola. That's when you have constant acceleration, your position curve looks like a parabola. So let's go back. And we know at 2 seconds, we should end up here. Oops. And so we're going to have some curve like that. Okay. Now, from 2 to 3, we have constant velocity. So we're and it's positive. So we're going to continue gaining or increasing our position. And from 2 to 3, we want to calculate the area under the curve in this region. I shouldn't have drawn my other axis so large. So anyways, the area in this shaded region here is just 4 times 1, which is, well, 4, right? And so, from 2 to 3 seconds, our position actually increases. I've run out of room, but hopefully you'll see this. So we increase linearly because we have constant velocity. In this region here, we have constant velocity. Okay, now from let's look at the next interval from 3 to 5 seconds. We have to calculate the area of this shaded region. Now there's 2 areas here. We can break this into 2 easier areas. There is a rectangle, which again I didn't draw very well. There's this rectangle here underneath this dashed line, and there's a triangle. So the area of the rectangle is 2 times 2, which is 4 meters, and the area of this triangle here, this one right here, is actually half of that, so it's 2 meters. So there's 6 meters here. So we have to, the change in position is 6 meters. So in fact, I really ran out of room here. We have to add 6 more. So in this interval, all the way up to 5, we go up 6 more. Now I don't have a scale anymore for my x-axis, but imagine it continues up, and this is where we end up with at 5 seconds. And again, note that the velocity is changing. In fact, the velocity is getting smaller. This is a result of acceleration over here. So our position versus time curve is not a straight line. It should be a parabola, and it's a different shape than the other one we drew. It's the velocity is getting smaller, so it's concave down instead of concave up like it was in our first 2 seconds over here. Okay, I'm sorry about that position versus time graph, but that's hopefully this helps, and good luck.